Good evening. Many of you are the proud owners of a refractor telescope which will allow you to observe planets like Venus. In this month's programme we look at the fascinating story of the refractor from its humble beginnings. The refractor consists of an object lens at the front of a telescope which focuses the light down the main tube and into the eyepiece where it is magnified. The focal length has a direct influence on the magnifying power of a telescope, so there are two important points to be made. Firstly, the magnification of a telescope changes as the eyepiece is changed. Magnification can be calculated by dividing the focal length of your telescope by the focal length of the eyepiece. Therefore, always start with your lowest magnification eyepiece and work upwards from there. A 2 times Barlow lens will double the magnification of whatever eyepiece you use with it. For example, using a telescope with a 900mm focal length and a 20mm eyepiece will give you 45 times magnification. Using the same telescope and eyepiece with a 2 times Barlow lens will give you 90 times, which is the same power as a 900mm telescope with a 10mm eyepiece. Secondly, it is not generally realised that the object lens, as well as forming and illuminating the image, also plays a part in magnifying it. The image is enlarged by a factor of 1 for each 25 centimetres, that's 10 inches of focal length, which led to the invention of the so-called aerial telescopes. For example, the telescope used by Hevelius in 1647 had a focal length of 150 feet, giving a magnification of 180. We'll be looking at these telescopes later in the programme. Studies of the reflection of light by mirrors go back a long way. Euclid wrote about it as early as 300 BC. There have also been reports of telescopes well before Hans Lippershey of Holland is reported to have made the first refractor. Robert Grosseteste, who wrote a series of books between 1220 and 1235, alludes to a method of making things a long distance off appear very close. Another hint came in the 13th century from Whittelow in Eastern Europe and John Peckham in England. Leonardo da Vinci, who was born in 1452, knew a great deal about lenses and mirrors, and his diary contains the significant comment, "Make lenses in order to see the moon large." It seems that in 1514, when he was working at the Vatican Hill, he was busy on some optical device which was so secret that he would not let even his craftsmen helpers grind the lenses involved. Whether Leonardo ever developed any sort of telescope, we will probably never know. There are various other vague reports of refracting telescopes constructed in the early years of the 17th century. For example, a Dutch optician named Zacharias Janssen is said to have made a 2-lens combination which magnified distant objects. However, he abandoned it because the images were upside down. For positive evidence, we have to wait until the time of Hans Lippershey, who offered his telescope to the authorities in Holland on the 2nd of October 1608. By 1609, telescopes were on sale in Paris and presumably elsewhere. They gave erect images and were used mainly for looking at distant objects such as ships out to sea. Astronomical observations were made by Thomas Harriot and others, including an English baronet, Sir William Lower, who used a telescope to look at the moon and compared it with a tart that his cook had made. "Here's some bright stuff, there's some dark, so confused all over," he said. The great pioneer was Galileo Galilei, who lived in Italy. Galileo first heard about the Dutch invention in the summer of 1609 and at once set out to make a telescope for himself. In his book Sidereus Nuncius, he later wrote that, "By sparing neither labour nor expense, I succeeded in constructing myself an instrument so superior that objects seen through it appeared magnified nearly 1,000 times, and more than 30 times nearer than if viewed by the natural powers of sight alone. During his lifetime, Galileo seems to have made about 100 telescopes, of which a few survive. Each had a convex object glass and a concave eyepiece, giving an erect image, but a very small field of view. It was Johannes Kepler, who was born in 1571, that first introduced a convex eyepiece, which improved the field size and the overall performance at the cost of inverting the image. As far as we know, Kepler did not actually make such a telescope. Christopher Schneider at Ingolstadt first did this around 1615, but Kepler's book Dioptris shows that as a theoretical optician he was superior to Galileo. Galileo saw the mountains and craters of the Moon, the countless stars of the Milky Way, the 4 moons of Jupiter, the phases of Venus, and the strange shape of Saturn. 2 of these discoveries were of special significance. The fact that Jupiter had 4 satellites showed that there was more than one centre of motion in the universe, which was in contradiction to Ptolemy's theory. The 4 satellites are still known as the Galileans, even though Galileo may not have been the first to see them. He may have been anticipated by a German named Simon Marius. Venus showed a complete set of phases from new to full, and on the geocentric theory this could never happen. It was in fact the behaviour of Venus which gave the final proof that Copernicus must be right and Ptolemy wrong. Galileo also observed sunspots, apparently by using his telescope as a projector rather than looking direct. Galileo's telescopes may have been low powered and by modern standards inefficient, but they were at least manageable. This was not true of the best refractors of the later 17th century, which were so incredibly clumsy that one wonders how they ever have been used successfully. The main problem was that of false colour, a problem that to some extent is still with us today, though in much reduced form thanks to the development of modern technology. It stems from the fact that light is a wave motion, and that what we normally call white light is a mixture of all the colours of the rainbow, from red through orange, yellow, blue and green to violet. Red light has the longest wavelength, violet the shortest. If the wavelength is longer than that of red light, it does not affect our eyes. We have in succession infrared, microwaves and then radio waves. Beyond the short end of the visible range, we have ultraviolet, X-rays and then gamma rays. Pass a beam of light through a glass lens and the different parts of it will be bent or refracted by different amounts. Red light will be refracted the least, violet the most. The result is that gaudy blue rings that may look beautiful but to astronomers are decidedly unwelcome will surround a bright object such as a star. The first attempts to counter this effect involved making object glasses of very long focal length, which certainly reduced the false colour nuisance, but which introduced new complications. Telescopes were so long, but they were so very clumsy. One observer who used them was Hevelius of Danzig, now Gdansk in Poland, who is probably best remembered for his map of the Moon, completed in 1647, and which was a considerable improvement on either Thomas Harriot's or Galileo's. His longest telescope, at a focal length of no less than 150 feet, to provide a monster of this sort with a metal tube would have made it far too heavy, and a paper tube would have been too flimsy. So Hevelius used a sectional arrangement. Each section of a tube was made up of 2 40-foot wooden planks fixed at right angles to each other to form a 2-sided trough, and wire stays braced the whole arrangement. It was hung from a mast 90 feet high are operated from below by means of ropes and pulleys. The eyepiece had to be moved by 5 millimeters every 4 seconds to follow the target object across the sky, and since the field of view was very restricted, this was in itself quite a problem. As I said earlier, it is not generally realised that the object lens, as well as forming and illuminating the image, also plays a part in magnifying it. The image is enlarged by a factor of 1 for each 10 inches of focal length. The telescope used by Hevelius had a focal length of 150 feet, so that it had a magnification of about 180 times. Next in line was Christian Huygens of Holland, whose first telescope had a 2-inch object glass with a focal length of 12 feet. Huygens was probably the best observer of the time, though he is best remembered today as being the inventor of the pendulum clock. Encouraged by Hevelius' success, he made a telescope of focal length 23 feet, and it was with this in 1655 that he discovered Titan, the largest moon of Saturn. In the following year, he studied Saturn itself and realised that the planet was surrounded by a thin, flat ring, instead of being a triple body as Galileo had supposed. This discovery was announced in 1659, and Huygens also made the first sketch to show any recognisable feature on the surface of Mars. His drawing shows the V-shaped feature, which we call the Syrtis Major, quite clearly, and since he recorded the date and time of the observation, this showed later astronomers that the rotation period of Mars is constant. The modern value is 23 hours, 37 minutes, 23 seconds. Huygens then progressed to a telescope with a focal length of 150 feet, which seems to have caused great interest among the citizens of his hometown. With another telescope, with a focal length of 125 feet, the object glass was held in a short iron tube and placed on a high pole. A groove running up and down the pole made it possible for the eyepiece to be raised or lowered as desired, and the image was produced by the lens was received in an eyepiece supported by a wooden stand attached to the free end of the thread linking it to the object glass. The eyepiece itself was handheld, which must have added to the operating difficulties. On a dark night, the observer shone a light onto the object glass and then searched around with the eyepiece until he could see a reflection, after which he could align the optical system. Clearly, there was a limit to the size of the aerial telescope. The French astronomer Adrien Azotte, who originally put forward the idea of setting up a national observatory in Paris, planned a 600-foot telescope and even made the eyepiece for it, but it was never built and would have been impossible to use. The Paris Observatory was duly established and was ready by 1667 and was the first of all the national observatories, apart from that of Copenhagen, which was opened as early as 1637 but was subsequently destroyed by fire. The first director at Paris was Garvone Cassini, an Italian who had already made his name as a very keen-sighted and accurate observer. It was he who discovered the main division in Saturn's ring system, still known as the Cassini division, as well as 4 of Saturn's moons, Iapetus, Rhea, Dione and Tethys. He also used aerial telescopes with objectives made by the well-known optician Capani. When Cassini arrived in Paris at the invitation of the French king, he was faced with another problem. The observatory building had been designed for appearance, not practical use, and inconvenient turrets meant that the view was hopelessly restricted. In the end, Cassini was reduced to taking his telescopes into the observatory grounds and working from there. Aerial telescopes were still in use well into the following century. Using one, Francesco Baiocchini in 1727 drew what he claimed to be a first map of Venus, even showing what were believed to be oceans and continents. though there can be no doubt that all these features were completely spurious. Even a modern telescope would show nothing on this cloud-covered planet, and it was not until the space age that we found out what Venus is really like. In 1677, Edmund Halley had taken a 24-foot focused telescope to the island of St. Helena to carry out the first systematic survey of the far southern stars, which can never be seen from the latitude of Britain. However, by then it was becoming clear that some sort of solution to the main problem would have to be found. In 1733, a wealthy amateur astronomer, Chester Moore Hall, hit upon the idea of making a compound object glass. He fitted together two lenses, one concave made of flint glass and the other convex made of crown glass. These two types of glass refract different colours in different ways, and the two errors tend to cancel each other out, producing a colour-free or achromatic objective. The false colour nuisance can never be completely eliminated, but it can at least be drastically reduced. Moore Hall, a modest and retiring country barrister, had no wish for publicity, but in the 1750s the matter was taken up by an optical worker named John Dolland. His theoretical understanding was better than Moore Hall's, and after his death in 1761, his son Peter founded what was probably the first optical firm in history. In 1765, he took one of his achromatic objectives to the Royal Observatory at Greenwich. Its performance was compared with that of the best long-focus telescope at the observatory, and the superiority of Dolland's lens was beyond doubt. The old aerial telescopes promptly became obsolete. Dolland's telescopes looked attractive, and from 1783 they were made with brass draw tubes, which were far better than the old paper-covered vellum tubes. When set up on well-made mahogany stands, they were easy to use and were fitted with slow motions. William Rutter Dawes was born on the 19th of March 1799. He was a clergyman who made extensive measurements of double stars as well as observations of the planets, and was a friend of William Lassell. He was nicknamed Eagle Eye. He set up his private observatory at his home in Haddam in Buckinghamshire in the UK. One of his telescopes, an 8-inch refractor by Cook, survives at the Cambridge Observatory, where it is known as the Farragut telescope. Over the last 150 years, he has been credited by astronomers for what we term the Dawes limit. Aperture is one of the main factors to consider when choosing any telescope, but resolutely the reflector provides a much larger aperture, and aperture is what matters in telescopes, since the resolving power or ability to separate close images is important. It can be worked out for any telescope by dividing the constant 4.56 by the aperture in inches. The answer is the resolving power expressed in seconds of arc, and is easily worked out thanks to the work of Dawes. A telescope that is 11.4 centimeters, 4.56 inches in aperture will just divide 2 points 1 second of arc apart. Reduce the aperture by masking it, and the 2 points can only be seen as one. Assuming the telescope to be optically perfect, no refocusing can divide the single point. During the late 1800s, the refractor continued in popularity. This was largely due to the work of Joseph Fraunhofer in Germany, who proved to be a genius at lens making, and it is doubtful whether his object glasses have been surpassed even now. One of his refractors, an equatorially mounted 9-inch refractor, had been sent to the Berlin Observatory, and it played a major role in the discovery of the 8th planet, Neptune. In the UK, William Herschel discovered Uranus in 1781, not because he was planet hunting, but because he was carrying out a systematic review of the heavens, in order to find out how the stars were distributed in space. Before long, it was found that Uranus was wandering away from its predicted path, so that an unknown influence was at work. Two mathematicians, John Couch Adams in England and Urbain Le Verrier in France, independently decided that the perturbations must be due to a new planet moving in an orbit well beyond that of Uranus, and each arrived at a position for it. Adams finished his work first and sent the results to the Royal Greenwich Observatory, but the then Astronomer Royal, Sir George Airy, took no action. Adams had only recently graduated from Cambridge, and it seems that Airy was loath to interrupt the regular Greenwich programme in order to go on what might have appeared to be a wild duck chase. Le Verrier finished soon afterwards, and unlike Adams, published his results. In 1846, a copy of Le Verrier's memoir reached Airy, who belatedly decided to organise a search. However, there was no suitable telescope at Greenwich, and so Airy passed the matter over to James Challis, Professor of Astronomy at Cambridge. Here there was a good 11.7-inch telescope, known as the Northumberland Refractor, after its donor. Challis was not particularly confident about the accuracy of Adams' prediction, and he was also preoccupied with other observations. In particular, he was following a comet, Biela's, which had caused a major astronomical sensation by breaking in half. Challis did not have a good map of the area concerned and did not follow Airy's instructions. He later admitted that he got over the ground very slowly. In the meantime, Le Verrier had sent his results to Berlin, and two of the astronomers there, John Gall and Heinrich d'Arrest, asked the permission of the observatory director, John Ennick, to use the Fraunhofer 9-inch refractor. Gall and d'Arrest identified the planet on the first night of their search. It was, of course, the planet we now call Neptune. Only later did Challis realise that he had recorded the planet twice in the first week of his own search, but he had committed the cardinal sin of failing to compare his observations. As soon as Neptune had been identified, other telescopes were turned towards it. One of these was a 24-inch metal mirror reflector telescope made by William Lassell, a wealthy brewer who had made an excellent reputation as a British amateur astronomer. The 24-inch showed Neptune well, and in a short while he discovered Triton, Neptune's largest moon. The 24-inch was dismantled after Lassell's death, but has now been reconstructed and is in use at the Liverpool Museum in the UK. It was the Neptune humiliation which induced Airy to order a large telescope for the Royal Observatory. The Northumberland Refractor is still at Cambridge, though the original objective has been replaced by a slightly larger one. By the second half of the 19th century, it had become possible to make large object glasses, and in 1862, Thomas Cook in England built the first of the great refractors, the Newall 25-inch, which still exists and is still in use. It is now at the Athens Observatory in Greece. Around this time, the first telescope-making firms were established. One of them was founded in Dublin by Thomas Grubb, and it was he who was responsible for the giant refractor, the 26-inch, for the Vienna Observatory in Austria. The contract with the Grubb firm was signed in 1875. The total cost of the telescope was £8,000, and it proved to be a great success. The Grubb firm was by no means alone. In America, Alvin Clark and Co. came very much to the fore, while in France there were the Henry brothers, Paul and Prosper. Another noted lens maker was James Cook, whose objectives are as fine as any ever made. During the 1880s and 1890s, the great refractors were dominant. They included a 36-inch at the Lick Observatory in Mount Hamilton in California, a 33-inch at Meudon in the Paris area of France, a 31-inch at Potsdam in Germany, and so forth. The largest of all was the 40-inch at the Yerkes Observatory in Wisconsin in the United States, masterminded by George Ellery Hale. The 40-inch is still the main telescope at Yerkes and is in use on every clear night. A new factor then comes into the reckoning. To an astronomer, seeing is all important. The steadier and clearer the air, the better the view. High altitude is obviously an advantage because there is less atmosphere above to cause trouble. Yerkes is on the shores of Williams Bay, but this was because Charles Yerkes, the millionaire of finance, said, insisted upon having the telescope in the general area of his home city, Chicago. But Mount Hamilton is well over 3,000 feet high, and the Lick 36-inch benefited accordingly. Virtually all modern observatories are sited on mountain tops, which may be inconvenient, yet it is essential. Seeing conditions were also paramount when Percival Lowell, a wealthy American amateur, made up his mind to establish a major observatory, mainly to study the planet Mars, which he believed to be inhabited. Lowell and his assistants carried out an exhaustive survey of possible locations in the United States and finally settled upon Flagstaff in Arizona, where the altitude is over 7,200 feet and the observatory is well above the worst of atmospheric haze and dust. Lowell ordered a fine 24-inch refractor from Alvin Clark and put it to good use, even if he did not succeed in establishing the existence of canals which he believed he had seen on Mars. There is something very attractive about a giant refractor, yet with very few exceptions, all the world's largest refractors are old. The Innis 26-inch at Johannesburg, the last telescope made by the old Grubb firm, was brought into use in 1926 and has been noted for its work on double stars, but its recent career has been rather checkered, and at one stage it was put out of action altogether. However, the Innis telescope is in the city of Johannesburg, where the light pollution is a serious hazard. The sky is never really dark, and this means that the main advantage of a large instrument, the ability to detect faint objects, is lost. There was another reason why refractors began to give way to reflectors by the turn of the century. There is a limit to the size of a working objective lens because the lens has to be supported all around its edge, and if it is too heavy it will sag and distort under its own weight, making it useless. We must also concede that although the false colour nuisance can be greatly reduced, it can never be completely cured. The largest refractor ever made had a 49-inch lens. It was built for display at the Paris Expedition of 1901, but the 180-foot tube could not be mounted in the conventional way. Instead, it was left horizontal and the light was brought to it by way of movable mirrors. Not surprisingly, it never worked well and it was never used for any form of research. Before long it was dismantled, and it is said that the object glass remains stored somewhere in Paris. The fate of a Grubb 41-inch destined for the Pulkovo Observatory in Russia was even worse. Before the objects could be installed, the mounting had rusted away. By the end of the 19th century, the whole situation was changing. The great refractors were in use, but it had become clear that the future of astronomical research lay with the great reflector telescopes, and that is another story. That's all we have time for this month. Please visit our website, Vimeo, where you can watch all the past shows of astronomy and space. And if you like this program, please share it with your friends and members of your local astronomical society. Until we come back next month, good evening.